Hello everyone, my name's Logan. Welcome back to the lecture hall. Today we're covering section 4.5, the summary of curve sketching. What is that? Well, we're going to learn how to graph. And we're going to learn all the stuff, all the fancy material we need to do a proper graph. So let's get into it. The first thing we need from our function, the domain. We need our domain because we need to know for the set of values for which f of x is defined. What do I mean by that? It's wherever your input, it is all the input values where our function works. Second, we need intercepts, x and y intercepts. So what are x and y intercepts? X and y intercepts are where they hit the x and y plane, right? Where it crosses through the y plane, crosses through the x path and plane, and there are sometimes multiple, sometimes there's none. Third, symmetry. We need to know if f of x is equal to f of negative x. What am I saying? F of x is equal to f of negative x. Because if this were the case, then the curve is symmetric, and all we need to know is the first half of the graph. What do I mean by symmetric? Well, that means it will have the same right side as it has left side. And obviously, I didn't draw those equal, but it was my attempt at it. Or, we need to know that if f of negative x is equal to negative f of x. And what will that give us? This would be an odd function, if this were the case, and it would give us a mirrored image across the y equals x line. So if we had something like that, it would look like that, and that would be the odd function. So, we need to know symmetry. What's next? We need to know asymptotes. We need to know horizontal asymptotes, vertical asymptotes, and now slant asymptotes, which we'll cover at the very end of our function. Fifth, we need to know our intervals of increase or decrease. Well, we know how to find those from our chapter 4 stuff. It is taking the derivative and plugging in numbers, and if it's positive, it's increasing on that interval. If it's negative, it's decreasing on that interval. And then, to follow into our next point, if it's 0, that would be a local max or a local min. So, into our sixth part, F, we need to know our local maxes and mins. And why do we need to know this? Because we need to know where the graph peaks and valleys. And then finally, we need to know our concavity and our POI, points of inflection. And with all of this information, what can we do next? Once we have all of that information, we can graph it. That's all we need. All we need. We need about, 1, 2, 3, 4, 5, 6, 7 things, but that's all we need to be able to graph it. We need domain, intercepts, symmetry, asymptotes, intervals of increase or decrease, local maxes and mins, and concavity and points of inflection. After that, we can completely graph our function. So, what's the definition of a slant asymptote? A slant asymptote occurs when the limit as x approaches infinity of f of x minus mx plus b is equal to 0. And m cannot be equal to 0 because that would kind of take away the purpose of it. And what is this saying? It's saying that as x moves, as f of x, or as x approaches infinity, f of x minus our line mx plus b will equal 0. So what's it saying? It's saying that f of x is equal, or nearing, because it's a limit, nearing the line. And we kind of get a visual of this, and we see our blue line here, and our green line is our slant asymptote. This occurs when our function gets closer and closer and closer to this line, but never crosses over it, and it never touches it. And that is a slant asymptote. And how do they occur? Well, they occur when the degree of the numerator is 1 more than the degree of the denominator. And the equation of a slant asymptote can be found by long division. What do I mean by this? Well, if we have our function, f of x is equal to x cubed over x squared plus 1, we see, okay, this is 1 bigger than the denominator, right? X cubed is 1 bigger than x squared. So, what is this equal to? If we do some long division, which I'm not going to do right now, but we find that x this is equal to x over x squared plus 1. Then we find that y is equal to x is our slant asymptote, right? Well, how do we get that? Well, if we look at this, what is this? X over x squared plus 1. If we take the limit of this as x approaches infinity of x over x squared plus 1, what do we get? 0. So we can see as this moves to 0, our function moves to just be y equals x, right? F of x is just equal to x. As x goes to infinity, this part gets smaller and smaller and kind of fades to nothingness. That was kind of dark. I don't know. And then we can see, okay, so this is our slant asymptote, because if we were to take the limit of x minus x over x squared plus 1 minus x as x approaches infinity, and so our b is 0 in this case, our m is 1. We did this, we get that it is equal to, well, x cancels with x, and we just get it's the limit as x approaches infinity of x over x squared plus 1. And hey, that equals to 0. And hey, that means our slant asymptote is defined at y equals x. And it all works through the math. So, that is all I wanted to cover in the lecture portion of the video. Let's transition to some practice problems. Alright, now on to the practice questions. We're doing number 1, and only number 1 because there's a lot to do. So, let's go through our checklist. Domain, intercepts, symmetry, intervals of increase and decrease, maxes and mins, points of inflection and concavity, and then G for graphing it all. So, what do we need here? Domain, first, we need to know what input values work for y equals x cubed plus 3x squared. Well, that's very easy because there's no divisor, there's no denominator, so there is no problems running into anything undefined. We don't have any fancy functions, we just have a polynomial, and this polynomial is, the domain of it is all real numbers. So, I'm just going to write r, this fancy r. But you could also write it's negative infinity to infinity. You could write that as well, but it's all real numbers. Now on to the intercepts. The x-intercepts and the y-intercepts. Well, first, how do we get the x-intercepts? Or, better yet, how do we get the y-intercepts? Well, it's just when y equals, or just when x equals 0, right? Because we plug in where x equals 0, because if we look at our graph, we get a y-intercept when x equals 0, and an x-intercept when y equals 0, right? So, we're just going to find what does y equal when x equals 0. Well, it's just equal to 0 cubed plus 3 0 squared, so 0. So our y-intercept is at 0. But what about our x-intercepts? Well, it's something a little more difficult. We set 0 equal to x cubed plus 3x squared. And what do we get? We get x squared plus x plus 3, okay? And then that means that our x-intercepts, x equals 0, 0, and negative 3. But we get rid of that second 0, and we just get it's negative 3. Okay, now onto our symmetry. Well, we always check at the lead leg of the function, I guess, and we see, or the highest degree polynomial, that's the proper term, I don't know why I said lead leg, and we see x cubed. Okay, so odd numbered are going to be odd functions, and even numbered are going to be even functions. So the symmetry, not super important for this problem, because we're going to have so much more information that it'll be easy to graph it without it, but I'm just going to say it's an odd function, so we can just do our checklist. Okay, now onto intervals of increase and decrease. How do we do that? Everyone knows. derivatives. Yes. So we take y prime. Y prime is going to be equal to, power rule, 3x squared plus 6x. We set that equal to 0 because we need to find our maxes and mins, right? And we do 3x squared, oh, that's equal to 3x times x plus 2, right? Yes. So then we find our maxes and mins are at 0 and 2, negative 2. But what we don't know is we don't know which one's the max, which one's the min, and then where they are increasing and decreasing. So what we have to do is we have to write a diagram. This is a derivative diagram, a slope diagram, whatever you want to call it, and it's to find the intervals of increase and decrease. So we have 0 here, we have negative 2, or they're supposed to go right here. Negative 2, 0. Okay, why did I write this? Well, we know there's a 0 here and a 0 here. And we need to find the intervals where it's increasing and decreasing. So we have to check less than negative 2, in between negative 2 and 0, and then greater than 0. So first we're just going to do 0. What's greater than 0? 1. We plug in 1 to our derivative, which was 3x times x plus 2. We plug in 1 and we get 3 times 3, 9. So it's positive, so it's increasing there. Okay, now we get a number between negative 2 and 0, negative 1. We plug it in, so we get negative, so we had, it was y prime equals 3x squared plus 6x, and which is equal to 3x times x plus 2. And now we plug in negative 1. Negative 1. So negative 3x times minus 1 plus 2. What is that? We get negative 3 times 1, which equals negative 3. So it's negative. So it's decreasing there. Now we plug in a number less than negative 2. Okay, not too bad. Negative 3. So we plug in negative 3. We get negative 3x, 3 times negative 3 times negative 3 plus 2. Well, that's negative 1 times negative 9 is equal to 9, so it's positive. So we found our intervals of increase and decrease. It's increasing from negative infinity to negative 2. Decreasing from negative 2 to 0. And increasing from 0 to infinity. And we have our maxes and mins because we know 0 is a minimum. How do we know this? A local minimum. How do we know this? Well, because it goes from negative to positive, which means it goes down, 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 and then it shoots back up, which means that at the little point at the bottom, that's a minimum. And then we know this is going to be a maximum because it's the opposite. It's positive, 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 and then negative, negative, negative. And so that's a max, a local max. Finally, points of inflection and concavity. Well, second derivative time. So y double prime is equal to 6x plus 6, which is equal to 6 times x plus 1, which is equal to 0 because we're trying to find our point of inflection. And we just find that x equals negative 1. So our point of inflection is negative 1. Okay, that's all well and good. Now that we have our point of inflection, which is negative 1, we plug in numbers greater than negative 1 and less than negative 1. So we see negative 1, okay, what's bigger than negative 1? 0. That's the easy one to plug in. We plug in 0 here. We get it equals 6, so we get it positive on this side, so it's concave up when it's greater than 0. And then we plug in negative 2, let's say, negative 2 into this, and then that's negative 6, so then this is concave down from negative 1 on. Okay, so now we can start to graph our function. How? Where should we start? Well, let's start at the y-intercepts. So we know the function hits 0, 0 at some point, and then we know what other x-intercepts we have. And we have an x-intercept at negative 3. Okay, and then we know our interval of increase and decrease. So we know it's going to go, it's increasing from here somewhere, and it's going to break the the x-plane, right? And then I just realized we didn't actually find the points of our maxes and mins, so we have to plug that in real quick to the original function. So we plug in 0, and we get 0 is our local min, and then we plug in negative 2, and we get negative 8 plus 3x plus 3 times 4, which is negative 8 plus 12, which is equal to 4. So then we find our local max is 4. And then it goes all the way up. And then, what else do we know? We know it has a local min at 0. And then it bounces back up again. And it's going to look something like that. Not exact, you know, but pretty close. And then we kind of see our point of inflection is right there at negative 1. And this is how you graph a function when you have all this information. So, general strategy for these problems is just follow the list. Go through it probably 10, 15 times, and when I say 10, 15 times, I mean 10 or 15 separate problems, and this will be very easy. It just takes up a lot of time. So, that's all I wanted to do for this video. Again, my name was Logan. Thanks for watching. Have a great day.